Welcome to video number 2 in Advanced Fluid Mechanics. So this is a breakdown here of what we're going to be covering in this video. Now section 2 is called Kinematics, and we call it kinematics when we're just interested in looking at the motion. So we won't be considering the forces that cause this motion in this section. We're just going to look at the motion first. Later on in the course, we're going to be doing what's called dynamics, and that's when we'll specifically be looking at these forces. But for now, basically what we're going to do is we're going to build the groundwork here, because ultimately we do care about how the forces influence the flow and different objects. But first we need to mathematically describe that motion. So we're going to be looking at things like displacement, velocity, acceleration, deformation, and rotation of these fluid elements. So once we know how to mathematically describe those, then we can look at the forces that cause them later on. Okay, so section 2, kinematics. And as I mentioned in the intro, this is just going to be the study of the motion without reference to the forces or stresses that produce this motion. So quick introduction on this slide here. It's a reminder about our coordinate systems. So we're all on the same page here as we start this section. So in A, we have what's known as plane Cartesian or polar coordinates. Shown with x and y axes, right? Or x1, x2 there for the plane Cartesian, or as r and theta for the polar coordinates there. B's are 3D Cartesian coordinates. With x, y, z, or we've got x1, x2, x3 there. We're using these in each case to define P, which is our arbitrary point in space. C is cylindrical polar coordinates. And there P is defined by this r, or the radius, and then we have this angle, phi, and then we use z as well for cylindrical. And in D we have spherical polar coordinates. Where we define P instead with this r for radius again, but then two angles, right? We have theta and we have the phi. And in that way, we can completely define the location of P. Okay, now we're going to start by talking about two different ways we have of describing fluid motion. They're known as Lagrangian, or particle description, and Eulerian, or field description. In Lagrangian, we can basically think of it like we're following each fluid particle along as it flows. So using this description, if we want to describe our flow variable, our independent variables are going to be time, and then the position vector of the particle at some reference time. So shown in the figure here is A, right here, denoted as the position vector at this time t equals 0. So that's one of our independent variables. Then we also have the time, t. So our flow variable, f, is a function of a, right, and t. That's how we would write that. Same thing for our position vector, where we remember these underlines are for vectors, right? It's kind of like I'm bolding them. And that there represents the location at time t of a particle whose position was A at time t equals 0. So it was right there, and then at time t will have its new location. So in Lagrangian, because we're using the perspective of the particle, the velocity and the acceleration are just the partial time derivatives. So we would just write that like this. So u for velocity equals the change in the position over time. Acceleration, right? Similarly, we would just say that's the change, right, in the velocity over time, which is then of course just the second order derivative of the change in position with the change in time, because we're looking at the particle and its identity is kept constant during the differentiation. In the Eulerian description though, we're not following the particles. Instead, what we're looking at is what happens at a point in space. So in this way, our independent variables are that point that we're talking about, denoting it in this case as r prime, and then our time, which we'll denote as t prime 2. And I'm just putting the primes there just to distinguish from our Lagrangian variables for now, just to make it clear in this example here. So our flow variables would be like written like this as a function of r prime and t prime. But because we're only looking at this location in space, if we take the partial derivative, that's only going to give us the local rate of change at this point, right? And not the total rate of change that the particle is actually experiencing. Okay, so now what we're going to look at is how do you actually write the derivatives in the Eulerian description so that they can give you the total rate of change. And a note just here before we do that, I think it's important to point out that Eulerian is the one that we most commonly use. Because especially as engineers, we're most commonly looking at a point in space or an object in space, right? And how that fluid influences that object. Lagrangian is only used sometimes, and it's for cases where we're interested in finding specifically the particle paths as they flow. So occasionally in things like combustion or multi-phase flows, but for the most part, you'll probably be dealing with Eulerian specification. Okay, so we are commonly going to want to be able to write this particle derivative, but in the field description, right? So this rate of change of things as the particle sees it, but we need to write it in the framework of observing the point in space. So to do this, we're going to look at how we compare these two different descriptions. We'll start by saying, okay, we have some fluid property at exactly the same position and time in both of these descriptions. So we'll write that like this. But what we want to do is we want to write the rate of change of this fluid property as experienced by the fluid or as seen by an observer who's traveling with the particle, right? Except we want to do it in field variables. So mathematically what we're saying is we want this, but with respect to the field variables, which as a reminder is Eulerian field variables. Okay, so we're really saying what are the r prime and the t prime derivatives that correspond to this change in the Lagrangian or the particle description. Okay, so we're gonna do this calculation at the same point and time, right? So we can equate, right? R prime equals r therefore, and t prime equals t. So then this is true, we have our field variable. If we expand this out, like A is this position, and this is going to be equal in the field variables as well. So we just wrote there to relate the two, right? We could also say that f is a function of the position of our particle, which is then a function of the location at this coordinate A. So like where it was at time t0 and then time. And so you see that helps us relate the two, right? Okay, so now we keep going. So we're going to differentiate because that's what we want. We want the derivatives. So we got to be careful to differentiate our dependent variables with respect to the independent variables. We're going to apply the chain rule as well. So I'll write that out here. Okay, and with this notation here, we've shown that we've covered everything off, right? So we're taking the derivative with respect to time. So the first term where we've had the r prime that didn't change, and then the second term we had the t prime that didn't change, and the a. So we've denoted all that. So this is our complete derivative, and we've used the chain rule to show it with respect to all the variables. And then we can examine these terms, right? And we see that t prime by t is just the ratio of timescales. So that we can make equal to 1. Just use the same timescale, like seconds or whatever. And this term right here, I've put the label here. So that's just the transformation matrix between the two coordinate systems, right? That's just saying how like r prime changes with respect to r, and we're not rotating or stretching this thing at all. So that's just going to be 1 as well, which is represented by the identity matrix with the elements from the Kronecker delta we remember from last video. And then we see this one here, right? So we're saying that's the change in the position with respect to time. So this we've already denoted previously. That is our velocity, right? We just wrote that out on the last slide. So therefore, if we simplify all of this, we have this here, and that's the total rate of change of our fluid variable, but represented in the Eulerian coordinate system, which is the one we're more likely going to want to use. Okay, so we have a name for this because it comes up all the time. So we call this the material derivative, also known apparently as the substantial derivative or particle derivative. And remember the 3 lines there on the equal sign means is defined by. So that's like the definition of the particle derivative. And this reminds us that that derivative is taken with respect to following a fluid element. So let's look at this now. So we have 2 parts in this. We have the local rate of change, right, at a given point, which would be 0 for steady flows, right, if we didn't have any change in time. Then we have the second part here, which is called the advective derivative. Because what that is that's the change in the fluid property F as a result of the advection of this motion. So that means the particle's moving from one place to another where the value of F is then different. And then we can just rewrite this at the bottom here in vector notation. Same thing though. And that's how you'll commonly see it. We don't have the primes there when we're dealing with our Eulerian coordinates because we only put them here to distinguish between the Lagrangian ones for this little example here. So that's how you're commonly going to see that, where the scalar product there here, right, the advective derivative, so that's just the magnitude of the velocity times the component of gradient of f in the direction of the velocity. And that gives us the total derivative, or the material derivative, denoted with those capital D's. And of course, we're going to use this a lot. We'll see this come up a lot. Okay, now we're going to look at the streamline, the pathline, and the streakline, which you may have seen before at an undergraduate level fluid mechanics course. But here at advanced fluid mechanics, we're going to review this, and we're going to make sure we have the equations so we can mathematically write the streamline and look at a few interesting things about them. So we define a streamline as shown here as they're instantaneous curves that are everywhere tangent to the direction field. Okay, now I'll use the figure to show how you get this equation because I think it's really neat to see where it comes from. So we have ds, which is an element of arc length along the streamline. S denotes streamline, so we have it shown here, and it has components dx, dy, dz, and then we also have the velocity at that point shown with this vector here, u, and we know the streamline has to be tangent to that direction of flow. So I'm going to look at it in the x and y direction here and trace out this little triangle. Okay, so because we're tangent, we have that triangle, but then we have also the velocity has to be tangent, right? So we have two similar triangles there. There's a few different ways to derive this, but I kind of like this visually looking at it the best. So then we know, therefore, for sure, the dy over the dx has to be at the same ratio as the v and the u, the y component of velocity and the x component of velocity, right? Same thing for all these directions. So what that means then when we rearrange that is that the following is true, and this is the expression that we use for our streamlines. Another common way to show that is that you can show that the cross product of the velocity vector u and ds are equal to 0 if this is true. Because if they're tangent, then that cross product must be 0. Yes, then we have pathline, which is also a valuable way of describing this, especially experimentally. And this basically you just follow a single fluid particle where it travels through time. So basically its path. So a single particle, you follow its path through time. So if we have steady flow, these two things are identical. Pathlines and the streamlines will exactly coincide, but not in unsteady flow. So they'll be different in an unsteady flow. So in this figure here, we have a body moving from right to left. And if you were to observe this flow by an observer who's stationary with respect to the undisturbed flow, then the flow pattern changes with time. So as this thing moves from right to left, right, you would have this streamline here. And then as it moved along, you'd have this streamline here, and then the streamline here. So the streamlines are like changing, right? But the path, so if we just took this point right here, so the path the particle would follow would be going along like this, right? Relative to a stationary observer, that's what it would look like. But the streamline, of course, use a slightly different color, is this here, which is tangent to the flow at that point in time, right? So you end up with the two that are different in an unsteady flow because the particle at that one point in time is actually going like that way, right? But then as the body moves through, what happens is the particle goes this way, right? So you have a difference. And then streakline is another concept that comes up a lot, especially for flow visualization. And it's defined as the current location of all the fluid particles, like basically a line of all the fluid particles that pass through a specific point. So this would be like if you injected a dye or smoke. So if you had like a smoke one in the wind tunnel, I can actually show you a video of that here. So the like tip of that smoke one is at a fixed point, and then over an interval of time, you'd follow all the little particles as they travel and you'd trace a line back. So again, in steady flow, all three, like as shown in this video, right? Whether I draw a streak line, which is connecting all of these, I draw the path line, which is a single path of a particle, or the streamlines, so a line tangent to the flow, all three of those are the same line in this case, because this is steady flow. Okay, now from here, we can talk about something that's kind of interesting. So the reference frame really matters, okay, in fluid mechanics. So this is kind of a cool way to show this, right? So a flow that's steady in one reference frame is not necessarily steady in a different reference frame, okay? So let's consider this object moving again. So the figure shown at the bottom shows the same object, but with two different reference frames. Okay, so we can think of this as like a ship moving through water. We're overhead, we're looking down on the ship, so it's moving like from right to left. And in A, this is relative to an observer that would be like on the riverbank, so stationary as this ship comes and moves past it. So the ship has this velocity u as it moves through, and as it comes through, what happens is it moves these particles out of the way, right? So at the front, we're moving these particles out of the way, like this, right? And we have the P that we showed before. At the sides, these particles will be pushed and come back to here, right? We can just sort of imagine this in your head as this thing moves. And at the back, we're getting this point where particles that have pushed out of the way need to come back in, right? To fill the space behind where the ship was just moving, okay? And of course, we're stationary on the riverbank, so as this thing moves through, right? So those all, they change with time because the ship itself is moving past us, right? So if we took one snapshot and the next, the ship would be a little further along. So all those streamlines would have then changed, right? Relative to this location. But on B, let's say now we're an observer on the ship. Now it appears to actually be steady, okay? Because on the ship, if you look down at the water around you, you'd see these streamlines here, right? So you'd just see the water moving like this, okay? And then you'd have it coming up to this, what we call the stagnation point, and then you'd have it moving around here. So it looks to you like it's steady flow. So for you, it doesn't change with time, right? At any time, when you look down at the water, you're still going to see those same streamlines relative to your position moving along with the ship. So you see two different observers, and we have unsteady flow versus steady flow. Now, what's really cool is if you took this vector u, right, that the ship has, and you just added it to any of these velocities here in A, you get the same pattern, right? So any velocity vector here, right? So if I took this one like right here, let's say, basically I can get that by taking the velocity that I'm seeing here, right? And I just add, right? I just add this vector here, capital U, right, to that. And then I get the same velocity that I had this point right here. Okay, and we can also see this at point P. If I erase some of this, okay, so point P over here has this velocity vector shown as u prime. Also shown in B at point P, right? There's u prime there. Okay, so if we add this capital U to that, like this, then we end up with this u, I'll do it in a different color right here, right? Which is the velocity that's in B, right? So if you take what's in A, right, and you add the u to it, you end up with the velocity vectors that you have in B. And a complete switch between one that's unsteady in A versus one that's steady in B, just by switching your reference frame. Okay, that's pretty cool, right? Okay, so now we're gonna look at strain. And one thing that's really important when we later take a look at the dynamics is that we're gonna wanna see later how these forces that we apply cause deformation of our fluid, or what's known as strain, right? So we define the strain as a change in length per unit length, just like we do in solid mechanics. And we define shear strain as how a 90-degree angle changes. And so this is what we're going to look at here. In solid mechanics, we would just say strain, but we're going to say strain rates here in fluid mechanics because it continues to deform. Okay, so how do we write this mathematically? So we want the rate of change of length per unit length. So from our figure, our length is delta x1. So per unit length, 1 over delta x1. And the rate of change of that length, and we're already using the material derivative here, right? Because we're following this fluid particle along, but we want to use the framework of our Eulerian description. So we can equate this to, in looking at our figure, so per time, the difference between how it's changed at t plus dt minus our original length divided by the original length. And just to be super clear, we can note that this a prime b prime is actually equal to ab plus b prime minus a prime in another color. So this is a prime b prime, and we can get that by saying we'll have ab plus bb prime, okay, and then we minus off this a prime chunk here, so we're just left with that, and they coincide. So just a little rearranging, our a prime b prime minus the ab then we have in our equation there is actually equal to b prime minus a prime. So I'll write that up here so we're really clear on that. It's easier to see if we're just really explicit about this. Okay, then rearranging, we have our 1 over dt, we'll leave it there. We have our AB, which is 1 over our delta x1. And then we have BB prime, which is here, right? So that's that distance it's traveled, right? So we're showing there the velocity plus the rate of change of the velocity, right, over this distance it traveled multiplied by time. So we can take into account how much it's traveled as it's gone from B to B prime. So we expand that out here, so we end up with U1 dt plus partial derivative. And then we subtract the A prime, which is the velocity it's traveled from this point to this point, right, where it had this velocity U1, and we don't have to account for that extra factor that the B had, right, because it had a different velocity because it was at a different location. So if we have a change in velocity along this direction, we're going to see this thing stretch or contract, right? So mathematically, so we need to subtract A prime, so U1 dt gets subtracted. And then these two will cancel off. We also have the cancellation of the dt and the delta x1. So that very nicely just simplifies to this here. I can write it over here, maybe it's just this. So we can write that in more general terms, which is actually a little bit tricky to do. So we'll use a subscript alpha. The reason we do that is because we don't want to imply summation, right? So we use these Greek indices when we don't want to say that we're summing it, but we need to use the same index, right? So this is how we would generally write linear strain rate in the alpha direction, okay? So we can also look at what's known as volumetric strain rate or bulk strain rate, which is actually the sum of the linear strain rates in 3 mutually orthogonal directions. So if we look at all the directions and we sum the strain rates, we end up with the volumetric strain rate. And we'll see, so I'll use a very similar method as to above. So I like to put a little cross through the V's when they're volumes, just to make sure we don't confuse velocities and volumes. So I'll do that here. So we're saying what's the change in the volume per unit volume, where we have a fluid element. Let's say it has sides like delta x1, delta x2, delta x3. So then we can define this delta volume as delta x1, delta x2, delta x3. Back to our equation, same thing. So we're per unit volume. Writing it out like that. And then our material derivative, we sub in again for delta V explicitly there. We just sub those in for the delta V's. We further simplify. And that's just a result of the properties of derivatives, right? So that simplifies like that. But then we've already done this, right? Like we did this one above. And so we know actually what that equals. And it's the same in all the directions. So writing again what we had from above, right? We know that that's, like I'll circle it. So we ended up with that for the one direction. So we have that. And then it's the same for the other directions. And then we would actually write subscript I. We do have the summation in this case, so that's what it equals. So that's the sum of the diagonal terms of the velocity gradient tensor, which is di ui over di xj. And this will actually help us later when we're going to derive the conservation laws, specifically conservation of mass. So it's really helpful for us to be able to mathematically write this deformation rate, right? So if we have a change in length per unit length, or if we have a change in volume per unit volume, this is how we express it mathematically. You can just sort of highlight that, like maybe put a box around this one or something. Okay, so in addition to this linear strain rate we just looked at, where we have objects undergoing normal strain rates, we can also have an object that deforms in its shape, right? And the way we define this shear strain rate is the rate of decrease of the angle formed by two mutually perpendicular lines on the element. So we can look at our figure for that. So we've had this change, right, from this angle here to this angle here, okay? And it's the rate of decrease of that angle is our shear strain rate. So because of the small angle theorem, we have this small angle d alpha, and that's actually equal to CA over C b. Because if you remember, small angle theorem tells us the angle is the same as the sine of that angle for very small angles. Same thing for the beta angle that's shown there too. And this depends, of course, on the orientation of this line pair that we pick, okay? So these lines are originally parallel to our coordinate system at time t, and then we have this change over time t plus dt. Okay, so let's write that mathematically. So we have the rate of decrease of our angle, which is defined by these two angles here. That's what it's decreasing by, and it's a rate, so it's that over time. And we can write that as follows. So it's 1 over CB, which is our delta x2, right? Looking here and here. And then for CA, A is defined right here. So it's how that velocity U1, right, has changed over that x2 direction multiplied by our time, and that C coordinate is right here. So our A coordinate minus our C coordinate, we end up with just this term. So to make sure that's clear, it's because the U1 dt's, right, from C to A would cancel, so we're left with just like that component there, which is right here. Exactly the same thing happens for our beta angle right here. Assuming you can follow the same steps, I'll just write it out, the exact same thing again. I'm getting low on space though. And close my brackets. And multiplying everything through, right, we see that these will cancel out, these will cancel out, and so will these. And again, we're left with this nice expression here. So it is as follows. So if we look at this shear strain rate expression, and remember for a second that our linear strain rate was the partial of ui over xi from the previous slide, we see that we can make something called the strain rate tensor. And then we define this, Eij is defined as this expression here. And then we see that the diagonal elements, the 1, 1, 2, 2, and 3, 3, those correspond to the normal strain rates, right? Those linear strain rates. And the off-diagonal elements are half of what we have in this expression here, right? For the shear strain rates. And then we see as well, this expression is symmetric. And so this really nice, concise way of writing the strain rate tensor is going to come in really handy for us as we look at more of the concepts in this course. Okay, now we're going to look at a concept that's called vorticity. And we're interested now in looking at how to describe the rotation of fluid elements. So fluid lines that are oriented in different ways are going to rotate by different amounts. So if we want to be able to define a rotation rate that means something that's not ambiguous, what we do is we take two mutually perpendicular lines and we calculate the average rotation rate of these two lines. And then what we end up with, this average, is actually independent of the orientation of this pair of lines, okay? For reasons of simplicity and to avoid factors of 2, what we end up doing is we make this value twice the value of the angular velocity, and this is what we call the vorticity of the element. So the vorticity of the element is double this average angular velocity. So what does that look like? Let's write this mathematically here. So we have the same figure that we were looking at for the shear strain rate, and this time we're going to define the average angular velocity about the x3 axis. So that average would be half of, and then we have the right-hand rule where the x3 coordinate is pointing like out of the page towards us. So the rotation of that d alpha, so it would be negative d alpha by dt, and then the beta is in the positive direction, so we would add that. Okay, and that would be our average angular velocity of this element. Now, an interesting thing to note here about rotation, we can stop and look at this for a second. The way it's shown in the figure, if our d alpha and d beta angles happen to be changing at the same rate, they would cancel each other in this expression, giving 0 for our angular velocity, because as you can sort of visualize there, they'd be changing the shape of the element, but not actually have any net rotation. So in that case, you'd have no rotation as we're defining here, but you would still have the shear strain rate and a change in shape as we saw in the previous slide. Now, just to write everything out really explicitly here, I'll just remind you that this d alpha element, because of the small angle theorem, is equal to CA over CB, right? Because the angle is also equal to the sine for small angle. So when I take the vorticity, I double this average, right? And I write that as this omega. So we double it, gets rid of the half. Then everything is 1 over dt from that expression. I simplify it the same way we did for the shear strain rate, where this CA, right, is this one, subtract this one. So we're left with just this part here. We divide by CB, which is defined in the figure, like right here, right? So let's divide by that CB first, and then we'll write out that expression from above, but it's negative now, right? I'll just put a little arrow, it's negative, right? So it's negative di u1 by di x2 delta x2, and we have our dt there, plus, and then the beta again is the exact same thing, so it's 1 over the delta x1, but it's positive. And then we multiply through and simplify all that, so the dt's multiply all the way through. Delta x2 is delta x1, same thing. So we are just in the end left with this simple expression that is this. Now we can see from, again, observing this, that we can use the definition of a curl of a vector, which we defined previously, to relate the vorticity vector to the velocity vector. So that looks like this, right? Or in the index notation, I'll box those, right? Because the vorticity expressions are important. So then we say something is irrotational if that vorticity is equal to 0, right? That's how we define irrotational. And that would require this to be true. When I is not equal to j. That's a convenient way to check for an irrotational flow. And then when we have irrotational flows, the velocity vector can be written as the gradient of a scalar function, because the assumption, we'll write it out here, phi is the scalar function. So that satisfies the condition we just defined here, right here. That condition is satisfied if that's the scalar function. All right, so this concept of vorticity is something that's going to be very handy for us as well. Okay, so next we'll look at the concept of circulation, which is basically the amount of fluid rotation within a closed contour or circuit. We're going to call that c. And this is defined as the line integral of the tangential component of velocity. And we would write that like this. And then we can extend this by looking at Stokes' theorem, which tells us that a line integral of u around this closed curve C is equal to the flux of curl u through an arbitrary surface A that's bounded by C, right? And this word flux, we generally use that to mean the integral of a vector field that's normal to a surface. So using the definition we have for vorticity and circulation combined with Stokes' theorem here, right? The vorticity was the curl of velocity, so we sub that in, therefore, and we get this expression here, relating circulation and vorticity. And therefore what that's telling us, that's the mathematical way of saying that the circulation around a closed curve is equal to the surface integral of the vorticity, which we can call the flux of vorticity, right? So we're saying the vorticity at a point equals the circulation per unit area. Okay, so that's how we define our two new concepts here of circulation and vorticity. Okay, now to develop another concept we're going to need to later describe things in advanced fluid mechanics is we're going to look at the relative motion near a point, and that's going to help us understand something called the principal axis. So we've just seen that fluid particles can deform and they can rotate, and now we're going to take a look at how do we describe the relative motion between two neighboring points. Okay, so we have point O, and its velocity is u. Then we have this neighboring point P with its velocity of u plus du. So then we would have the relative velocity at time t. We write as follows. And then we have this term here, which is the velocity gradient tensor, as I've noted there. And we can decompose this velocity gradient tensor, as we've seen in the previous video, into symmetric and anti-symmetric parts. So that would look like this. And then we can see that we can write that this here is our strain rate tensor. And then this here is our rotation tensor. Call that Rij, which is defined as this. So this actually equals this. Okay, now Rij, we can see from this definition, is antisymmetric. So that means its diagonal terms are 0 and the off-diagonal terms are equal and opposite, okay? So it therefore has 3 independent elements, R13, R21, and R32. But we see from our indices, right, that like R, if I plug in 2, 1 here, right, that equals omega 3. If I plug in 3, 2, it's omega 1. And then if I plug in 1 and 3 for I and J, it's omega 2. So I can actually write this out like this. So I can write the rotation tensor in terms of the components of the vorticity vector like this. And we can see that, so you can just go back and look at our definition of vorticity and you'll see that this is what happens. So if we want to write that, we can write that out in index notation a little more simply, maybe like this. Okay, and that's how we get our rotation tensor. Now a different color for this, so we're going to sub back into this DUI expression. So we then have as follows. Which we can also write like this. Based on our definition of cross product, right? We have the I component of the negative of the cross product. Now looking at this second term here, so we know that the velocity at a distance x from some axis of rotation of a body that's rotating rigidly at some angular velocity is denoted as this angular velocity crossed with that distance, right? So the second term here is the relative velocity at point P due to the rotation of the element at some angular velocity of omega over 2. And of course, the angular velocity is half the vorticity, right? So I've written that out here. So this second term is the relative velocity at P due to rotation of the element at this angular velocity, omega over 2. And the first term, we can see that's the relative velocity due only to the deformation of the element. Okay, so this term, right, I've made a little note of that right here. So that's the relative velocity P due only to deformation of the element, right? And that's how we get the relative motion between these points P and O, right? Okay, next we'll look at the concept of the principal axes. So the deformation of an element actually becomes really simple if our coordinate system coincides with the principal axes of the strain rate tensor. Okay, because the components, right, of this tensor E, they change as the coordinate system is rotated. And what happens is for a particular orientation, so as we rotate this thing, there's going to be a coordinate system, right, where the symmetric tensor only ends up having diagonal components. And that's what we call the principal axes of the tensor. Okay, so it's the coordinate system where this tensor only has diagonal elements. Okay, so looking at our equation we just had, so if we're looking at the deformation part, if we denote now the variables in the principal coordinate system by an overbar, so in the figure, right, if we have our principal axis here, we use this overbar for like x1 and x2 there. Okay, now let's say that's the principal axis where we only have diagonal components. So we can write this first term in this equation like this. So okay, so we have like E11, E22, and E33 with the bar over them. So those are the diagonal components in the principal coordinate system, right? And those are called the eigenvalues of E. So writing out explicitly the 3 components would look like this. Now we can take a look at this, and in looking at this mathematical expression, it tells us actually what's physically happening here, okay? So if E11 is positive with a bar over it, okay, then this equation shows that point P is moving away from point O in the x1 bar direction at a rate that's proportional to the distance dx1 bar, okay? So if we consider for a second all the points on the surface of a sphere, we look at our figure for this, the movement of P, okay, in the x1 bar here direction is therefore the maximum when P coincides with M, right? Where this dx1 is a maximum, right? You see that? Because it's proportional to the distance dx1. So that's the maximum dx1 can be is that right there, okay? And it's 0 when this P coincides with this N here, right? Because now that dx1 distance is 0, right? From point O. So in this figure, right, we have this shape here. You can see this new shape with this outline here, right? So therefore that'd be the new shape, right? So this diagram here is showing a case where E11, right, is greater than 0 and E22 is less than 0, right? Because we have E22 here, right, compressing that, and we have the E11 stretching or expanding that side, okay? So you see this is it mathematically, and then that's what it corresponds to physically, right? I think it's really important we have that sense of how these mathematical expressions relate to the actual physical scenario we're dealing with. What we're looking at here is in a small interval of time, this spherical fluid element around this point O becomes an ellipsoid, right, whose axes are the principal axes of our strain tensor, E. So you see that's the change that we're dealing with in this flow field. So in summary, the relative velocity in the neighborhood of a point can be divided into two parts, right? So we've seen it has one part due to the angular velocity of the element and the other part that's due to the deformation, okay? And a spherical element will deform to an ellipsoid whose axes coincide with the principal axes of the local strain rate tensor, all right? So that's this cool relationship, this principal axes, the components where our tensor has only diagonal elements can show us the coordinate system, right? Where we have our deformation acting, okay? And I think it's really neat to see that, right? Okay, so now what we're gonna do is we're gonna look at the rotation and the deformation that results from different type of flows. So we're first gonna look at parallel shear flows here. Okay, so we've got a figure of our parallel shear flow, the mathematical description up here as well. So we're showing that U1 is a function of the x2 direction. So we see U1 changing as we move through the x2 direction, right? Okay, so our velocity gradient, let's denote this with gamma. It's a function of x2, and that's defined as our velocity gradient, du1 dx2. Okay, so now we know from our equation above for vorticity, which I've shown here, we have the following three components, like omega1, omega2, and omega3, and the only one that's gonna have a non-zero component is omega3 here, right? Which is just gonna be a negative partial of u1 by partial of x2. So we can write that like this. So omega 3 equals negative gamma. Okay, now we look at our figure. We look at this element A, B, C, D. So we know we can relate now our math to our physical scenario, and we know that this line element AB has an angular velocity of negative gamma, right? BC has an angular velocity that's 0, right? Because it's in the flow direction right there. So therefore, the overall angular velocity is negative gamma over 2, right? Because it's half the vorticity, right? And this doesn't depend on which elements are chosen to compute it, okay? So that's how we get the angular velocity. However, when we look at the strain rate, this does depend on the orientation of the element, okay? Okay, so from our definition in the previous slides, the strain rate tensor of our element shown here is A, B, C, D, with our sides parallel to the x1 and x2 axes, is this. Okay, and we remember what this means. So therefore, element A, B, C, D undergoes shear, but no normal strain, right? Because it's got zeros in the diagonal. But if we rotate this 45 degrees, actually we have this property that a symmetric tensor with 0 diagonal elements can be diagonalized by rotating the coordinate system through 45 degrees. So then if we do that, we'll see that this is going to correspond to our principal axes, which we're going to denote with the overbars, right? So I'll circle that here and here. And the strain rate tensor for that is this. Okay, that's what we end up with, right? Rotated 45 degrees. And so again, we want the physical meaning of this. So this means that we have like linear extension rate, right, at E11 there with the bar of half gamma, and a compression rate at E22 here, right, negative half gamma. With no shear, right? So this is a little squirrely to think about, right? But the figure is going to make this clear, I think. The figure makes this really cool to see. So we see when we look at A, B, C, D, right? What we had was only shearing, right? So then A prime, B prime, C prime, D prime, we see has not had any normal strains, but it has had shear, right? Because it went from this position, and we see that that angle has changed, okay? Now, when we look at the element PQRS, right, it's rotated this 45 degrees initially. Now we can see that it does not have a change in angle, right, when it's P prime, Q prime, R prime, S prime as a result of this flow, but it has stretched along this direction, right, and compressed, right, along this direction, okay? So like the PS is elongated and the side like PQ has contracted, but the angles are still the same, right? So that's like visually we can see what's happening, right, with these strain rate tensors and the diagonal versus the off diagonal components, right? So in summary, our element ABCD in a parallel shear flow will experience only shear but no normal strain, whereas the element PQRS experiences normal strain but no shear strain. However, both of these elements rotate at the same angular velocity. Okay, now that's pretty sweet to see, right? Okay, now we're gonna look at the same thing, but instead we're gonna look at vortex flows. Okay, so we're gonna use these descriptions we have now to understand vortex flows. So we're first gonna look at what's known as solid body rotation. Okay, so for this, we're going to consider where the velocity is proportional to the radius of the streamlines. All right, so using polar coordinates like r and theta, then we can write the velocity in this flow like this. Okay, so our tangential velocity is proportional to the radius of the streamlines, and we have no flow in the radial direction. Okay, and this omega naught is a constant here that's equal to the angular velocity of the revolution of each particle about the origin. Okay, and we'll see that in a second. So we can get the vorticity components about the z-axis in polar coordinates, and we've of course already defined the vorticity. So to have it in polar coordinates, you can just look that up. So I've listed here the omega z component, right? And then I'm sure you can see that if I take this, right, and I sub it in there, that's like omega naught like r squared, right? So then I take the partial derivative of that with respect to r, I end up with 2r omega naught divided by r, so that's just 2 omega naught, right? This one is 0 because UR is 0. Okay, so that's the vorticity component about the z-axis, right, in these polar coordinates, which makes sense, right? Because that's based on how this thing is rotating, right? Omega naught's equal to the angular velocity, right? Like the speed of rotation of each particle about its own center. And so we can see this by looking in the figure. So if we look at element ABCD, right, at 2 successive times, so ABCD moves to this like A prime, B prime, C prime, D prime. So we see that 2 mutually perpendicular fluid lines like AD and AB both rotate counterclockwise about the center of the element with speed omega naught. And the time period for one rotation of the particle about its own center equals the time period for one revolution about the origin, right? So the center of the element would be like right here, and the origin course is right here, right? We can also see from this that the deformation of these fluid elements is 0, right? So each fluid particle retains its location relative to the other particles. And so a flow that's defined like this is called solid body rotation because the fluid elements behave just like a rigid rotating solid would behave, right? Now we can look at the circulation too. So we can sub in for this, right? Integrate from 0 to 2 pi. Velocity is U theta. We have R times D theta. Our streamlines are in the theta direction. None of that's a function of theta, so we just integrate, and that's 2 pi times R U theta. And we sub in for that, we have 2 pi R squared omega naught, subbing in for u theta. And that shows that our circulation is equal to the vorticity, 2 omega naught, times the area, which we remember, right? That was the relationship that we developed for the circulation. Okay, so I think that's pretty cool too. That's solid body rotation. That's how we describe solid body rotation. So let's look at another one. Okay, so now we're going to look at what's called an irrotational vortex. Okay, so we're going to notice here that circular streamlines don't actually have to imply that a flow has to have vorticity everywhere. Okay, so we're going to look at this irrotational vortex, which sounds kind of like an oxymoron, but we're going to do this by considering the flow around circular paths where the velocity vector is tangential, okay, and inversely proportional to the radius of the streamline. Okay, so that's shown in the figure here. So our u theta is C over R. Okay, so as the radius gets bigger, the velocity gets smaller, right? So we write that out here. Again, we have only the tangential component. So we again can sub in, see that this term again is 0. When we look at the vorticity, we plug this in here, right? So that just ends up being C, and we take the partial of that with respect to R, so we end up with 0. So what we end up with for vorticity is actually, let's write it as like 0 over R, okay? So this shows that the vorticity is 0 everywhere, but I've written it like that so we can see that except at the origin, okay? Where it can't be determined from this expression, okay? So we can, however, figure out the vorticity at the origin by considering the circulation around a circuit that encloses the origin, okay? From our relationship between circulation and vorticity. So we can actually look at a circuit of radius R. Circulation is going to be same like before, 0 to 2 pi u theta, and then we have r d theta, right? And then this is again going to be 2 pi because none of that's a function of theta times c when we plug it in this time, right? So this shows that the circulation is constant and it's independent of the radius, right? But remember the previous case of solid body rotation, our circulation was proportional to r squared. But in this case, the circulation's completely independent of the radius. So the circulation around a circuit of any shape that encloses the origin is actually 2 pi c. But if we think about the Stokes theorem for a second, that told us that the circulation was equal to the vorticity flux, basically. So the left-hand side is not 0, which implies that somewhere the vorticity also has to be not 0, somewhere in this area enclosed by the contour. Because the circulation is independent of r, we can shrink the contour without altering the left-hand side of the equation. So in the limit, the area approaches 0. So that means the vorticity at the origin has to be infinite, okay? So that this term here has a finite non-zero limit at the origin, okay? So that's mathematically showing us that flow represented by this type of velocity field here, it's irrotational everywhere except at the origin where the vorticity is infinite. And we call this flow an irrotational, or actually it can also be known as a potential vortex. Now, although the circulation around a circuit that contains the origin in the irrotational vortex is non-zero, a circuit that doesn't contain the origin is 0. We can show this, right? Let's work this out. So if we take our element ABCD and we do the circulation, these line integrals around BC and DA, right, across the streamlines will be 0, okay? So we can actually sub in like we did before. And this AB1 we write as negative because U and DS are actually in the opposite direction, right? For AB, and then for CD, we're at an additional radius outward, right? And we're going over this range delta theta here, shown in the figure. Now u theta times r is a constant, right? Is c. So therefore, this will just be u theta times r, right? Minus u theta times r, and that is just equal 0. Okay, there we go. So a 0 circulation around ABCD is actually expected because of Stokes' theorem, right? And the fact that the vorticity vanishes everywhere within ABCD, okay? Because it's irrotational everywhere, right? Except the origin. So everywhere within ABCD, we have 0 vorticity. So that all makes sense, right? And I think it's kind of fun to reflect on this visually. Like this picture kind of shows what's happening and this idea of it being irrotational, right? So if we look at like AD has become A prime D prime. So this like little bit of rotation sort of that way, right? And then BC, as it moves, becomes B prime, C prime, with like a little bit of rotation that way. And so the net effect is that it hasn't rotated at all, right? So we're seeing, that's why we're seeing this vortex, but it's actually like irrotational. So we look at those two, we'll sort of highlight them here, like that's what it becomes and that's what it started as, right? And so it's kind of wild to think about that actually rotating around, and that's how the shape changes as it rotates. And that's a visualization of it being an irrotational vortex. So that's pretty cool, right? Okay, so that's an irrotational vortex. Now we're gonna move on to one more kind of vortex here. Okay, so this last vortex is known as a Rankine vortex. Now, real vortices that you might see, for example, when your bathtub is draining or in a huge storm like a cyclone, what they actually have is a core that rotates almost like a solid body, and then an approximately irrotational far field. So visually, that would be shown like in A here. Okay, so these real vortices would have velocity distribution that looks like that. And we know a rotational core has to exist because the tangential velocity in an irrotational vortex has an infinite velocity jump at the origin. Okay, so we couldn't have that. So you have to have this rotational core. And we can idealize this type of behavior with what we call the Rankine vortex. So this Rankine vortex here, the vorticity is assumed to be uniform within this core R here, right? We have this vorticity shown here, and then it's 0 outside the core. So it's irrotational outside the core. So you end up with this here, Rankine vortex, that we can use to sort of approximate our real vortices. And we've seen how to mathematically write, these two different types of vortices here that we're combining to make the Rankine vortex. Okay, so that will help us out in describing the behavior of real vortices, right? It'll give us somewhat of an understanding of how they work. Okay, so in summary, what we looked at here in video number 3 was section 2, which is called kinematics. And so here we were describing the motion of the flow without considering the forces at this point. We'll do that later on. So we looked at two different ways of describing fluid motion, the Lagrangian and the Eulerian descriptions. We looked at how to mathematically describe a streamline. And then we looked at how fluid particles can stretch or contract, and how do we describe that mathematically, which is known as linear strain rate or our normal strain. Then we looked at how they change shape through a change in the angles of our fluid element and describe that mathematically, which is known as our shear strain rate. We also looked at the rotation. So how do we describe fluid particle rotation, which is known as vorticity? We also looked at then the related concept of circulation. And then we looked at the relative motion between 2 points and how we can define a principal axis to see the direction that the deformation is occurring. And then we closed by looking at parallel shear flows, and we saw how all these descriptions of the deformation and the rotation could apply to an actual flow. And then we did the same thing with some vortex flows, and we saw some really cool ways of describing a few different types of vortex flows, including an approximation for real vortices. Okay, so that's all for video number 3. Thanks for watching.